Hello and good morning. I am Sanjay Kumar Roy, PhD scholar, Lovely Professional University, and Head Power Distribution, OMQ Division, Tata Steel Limited, India. Welcome to Csscc 2021, the 13th International Conference on Circuit Systems, Signal Processing, Communication, and Computers. It is being held at Athens, Greece, starting from November 26th to 28th, 2021. The title of my paper is like this: An elegant method of analysis for the BJT amplifiers using floating admittance matrix. The author of this paper is myself, Sanjay Kumar Rai, Dr. Kamal Kumar Sharma, and Dr. Brahmadev Prasad Singh. Next. The abstract of my paper is like this: The floating admittance matrix FM is an elegant, neat, illustrative, and simplified technique for analyzing all configuration of the BJT amplifiers, starting with the maneuvering of the FM of the phase splitter circuit. The conventional analysis method requires a small signal equivalent circuit and then conventional tools, either KCL, KVL, or Thevenin, Norton, etc., are used for the analysis. The researcher has to guess which conventional tool suits better than the other for any particular circuit, whether active or passive. The proposed technique is equally useful for all circuits. In the FM method, once the device matrix is known, rest of the circuit can be embedded in it by inspection. The sum property of this matrix provides a check to know whether FM has been written correctly to proceed further or not. The keywords of this paper is like this: BJT, Csscc, floating admittance matrix, hybrid model, hybrid pi model, and T model. Next. We will go like this. First, introduction, the model development of BJT, then BJT phase splitter amplifier, then common emitter amplifier, common collector amplifier, then common base amplifier, conclusion, and references. Next. Introduction. There are several methods of mathematical modeling available in the literature based on the equivalent circuits approach. We have suggested an elegant mathematical modeling approach for both active device and passive circuits, called the floating admittance matrix model. As the word is spelled floating, it does not have any reference terminal in the analysis and design of any circuit, whether active or passive or mixed of the two. The floating admittance matrix model has been developed for the BJT to demonstrate the simplicity of the method over the other conventional technique. The outcome of the developed mathematical model has been used for any amplifier configuration that corroborates the result obtained in the available literature, overriding in the simplicity. Next. The background of the article forms the basis for arriving at the solution of circuits containing two or more than two BJTs or even MOSFETs and BJTs in different configurations. It is likely that one can make mistakes in putting the small signal equivalent of the entire complicated circuit, which can lead to an erroneous solutions. Additionally, a researcher must be able to guess for a particular circuit which conventional tools, KCL, KVL, Thevenin, and Norton, etc., become suitable for arriving at the solution with ease. The history of the development of FM using hybrid small signal equivalent circuit of the devices and its application in deriving all types of transfer and self-node functions of any amplifier configuration dates back to 1978. However, we developed the FM of the active device using recent trends in the small signal model of the devices, that is T and hybrid pi, and used it in arriving the solution of all types of transfer functions of different configurations of the amplifier with ease in this article. Next. We aim to derive all types of transfer function of all the BJT configuration, starting with a properly biased AC circuit of a phase splitter amplifier shown in figure 1. Before we start the analysis of any configuration of the BJT amplifier, we develop the floating admittance matrix in register RE in hybrid pi and hybrid HE model of the BJT. Among these models of the hybrid pi model is versatile. For this reason, we will take up the development of the floating admittance matrix, starting with T model and then R pi and finally HE model. To indicate the superiority of the floating admittance matrix approach over the conventional method of analysis, we derive all types of transfer function of the amplifiers for a comparison. Next. Figure 2a simplifies as figure 2b with forward biased dynamic resistances of base emitter junction diode along with a controlled current source beta IB. The input and output side of the BJT in figure 2b has to be isolated for the ease in the analysis. The isolation of the input side to output in figure 2b is achieved using the generator splitting theorem as in figure 3. The current at the base point are the same before and after splitting the current source in figure 3. The algebraic sum of the current at the base point equal to IB plus beta IB, which is equal to the emitter current IE that flows through the dynamic resistance of the diode RE, and then the control source beta IB is left open, resulting in figure 4. Next, the input resistance is seen through the base terminal of AC configuration in figure 4, results as VBE equal to IRE and then equal to RE 1 plus beta into IB. Rin in CE configuration is R pi as in equation 1 and Rin in CB configuration is RE as in equation 2. Similarly, the reverse bias collector base junction offers very large output resistances. R naught obtained using the early voltage equation. This R naught is included in figure 4 to complete the large signal equivalent circuit of the BJT. The derivation of the floating admittance matrix of the BJT assumes 3 digits 1, 2 and 3, assigning it to the base collector and the emitter terminals respectively. Hence, all terminal voltages and currents are expressed using these 3 digits in further analysis from figure 4. As we can see that IB that is equal to I1 is in equation 3, then I2 is IC that is in equation 4, and then next I1 plus I2 applying KCL, I1, I2, I3 equal to 0, then I3 is equal to minus I1 minus I2 equal to, as in the, we can see that I3 is equal to, is given in equation number 5. The arranging equation 3 to 5 in the matrix form yields the floating admittance matrix. It is given in the reference 10 to 14 of BJT in G equal to 1 by RE model as I1, I2, I3 and G by 1 plus beta, 0 minus G by 1 plus beta, Z, Z naught minus G minus G naught. Here we can see that the summation of all the rows and all the columns is equal to 0. It means that this equation is correct and we can proceed further. The simplified floating admittance matrix of BJT in RE model is, we have taken G naught Z by 1 plus beta as Z dash, then 0, then minus Z dash, and so forth. Here RE is equal to BV by IV, IE, BV by IC is equal to IE by IC, then finally alpha by GM. G naught equal to G dash equal to G 1 plus beta, G equal to 1 by RE, G naught is equal to 1 by R naught as in seen in equation 8. Next. Now the FM of BJT in hybrid pi model. Similarly, as seen in the figure 5, the simplified circuit of hybrid pi model of the BJT, the floating admittance matrix of hybrid pi can be obtained by analyzing figure 5. Here also we can see that I1, I2 and I3 as shown in equation 9, 10, 11, and then arranging 9 to 11 yields the matrix of the circuit as equation 12. Next, FM of BJT in S parameter model. Here we can see that I1, I2 and I3 as equation 13, 14 and 15, and arranging this 13 to 15, arranging equation 13 to 15 yields the floating endurance matrix as equation 16. Next, the floating endurance matrix of BJT in RE, RPi, HE models are available in equation 7, 12 and 16 respectively. Now we can develop the BJT phase splitter amplifier equations. To analyze the BJT phase splitter circuit of figure 1, the following admittance matrix of the BJT in the hybrid pi model of equation 12 is used as it is versatile. The overall floating admittance matrix of active and passive elements present in figure 1 results in 10 to 17. It's defined in 10 to reference 10 to 17 as given in equation 17. Here, where G pi is IB by VV, G is equal to 1 plus beta into G pi, R pi is equal to 1 plus beta into RE, and GL equal to GZ plus GL1. Similarly, we can formulate the equations for common emitter amplifier, common collector amplifier, and common base amplifier. Note, all floating admittance matrix and related equations, figures, references, and detailed explanations are available in the paper. Next. Conclusion. The floating admittance matrix method of analysis is very simple. Anybody with a little knowledge of electronics and the matrix maneuvering process can quickly analyze the circuit. Additionally, the floating admittance matrix zero-sum property provides a self-check before further analyzing the circuit. The methods does not require a small signal equivalent circuit. All transfer functions of any circuit use only cofactors, ratios, so that calculation can be accurate without any approximation. Next, these are some of the references which is published in the article in the journals and presented in the seminars. Thank you. Once again, remind that all figures, equations, and references are available in the original manuscript of the research paper. Thank you very much for listening so nicely. Thanks.